good start. Thank you very much, Candice. So, and thank you for the invite to speak today. So today will be a few different areas. I think where we're going to start off is talking about how polymer AM is used across the automotive sector. I'll dip a little bit into what we do at Jaguar Land Rover or JLR. I'll use those interchangeably if that's okay. And also what other OEMs in the industry are doing, and then really dive into a little bit what's limiting this further adoption of AM. We've been talking about AM in the automotive sector for a long time, and there's even a lot of people today have also mentioned how AM is so well suited to the automotive sector, but it's not maybe necessarily seeing the uplift that we might all hope, but we hopefully will get there soon. So I'm going to go through a few examples of where polymer additive manufacturing is being used currently in the sector, and why we've used it, and some brief examples. What you'll see is hopefully some of you have seen some of these examples before, and some of them will be new to you. I think what in general a comment from me about automotive examples, especially in the polymer AM space, is I would say 5 years ago, we were seeing a lot of the OEMs publishing these new pieces of work they were doing around polymer AM, and that's gone down significantly recently. I don't think that's because polymer AM isn't happening in automotive. It's happening more than it has ever happened before, but it's becoming more business as usual, and it's becoming a little bit more proprietary and a little bit more, this is so good, we want to be using it ourselves, and we don't necessarily want to be spreading it as wide and as far as we are, which is a bit of a pity, but it also shows how AM is becoming so important to these automotive companies, where it really becomes critical to their business. So this example is a small part, and it's used in the Tahoe vehicle for GM.
Luke, I'm really sorry to interrupt. Are you meant to have slides up at the moment?
Oh yes, I am. That's a good point. There we go. No, wrong. Can we see the slides now?
Yes, perfect.
Yeah, perfect. Thank you for that, Candice. So some failure mitigation. So GM have been manufacturing this part, and they manufactured this part only for about 3 months worth of production, but that equated to 30,000 vehicles or 60,000 parts. So these were HP printed parts using a TPU material, and they were essentially acting as a seal on vehicle. So the vehicle program was going along, and then they found a late problem with their spoiler meeting to the rear tailgate, and therefore recognized a part needed to be manufactured. That part via traditional injection molding or something similar would take too long for that tool to be designed and to come up and start producing parts as quickly as needed, and therefore AM is to some extent acted as this failure mitigation route, where we can produce parts quickly and we can go through trials very quickly to get them on a vehicle, even be that a customer vehicle. It's not the only example, but it's really one of the examples where GM were unusually, they were quite honest about it, and they came out and said, this is what the problem was and this is how we're going to fix it. And it's a really good example of AM at quite large production numbers, but still those, although it was 30,000 vehicles, that only covered them for about 3 months of their production. So it tells you some of the production numbers certain vehicles in the automotive sector are hitting. As we go through, we'll see some of those situations where we don't need quite as high numbers. So then going from where we've used AM as, okay, we need something quickly, we've got a problem, there are also more and more examples of where we've used additive manufacturing as a as planned. So from the beginning, automotive companies have planned the use of AM in their vehicles. There are a wide range of examples of these. There are some JLR examples as well as some other automotive OEM examples, and we'll touch upon just a couple of these. So the Lamborghini Urus will come at the end of the presentation. We'll also come all the way back to this, where we'll talk about how parts is used and how they've managed to get that to market. But this part is a fuel cap, and it's manufactured for their Lamborghini Urus or their SUV model, and it's Lamborghini's highest selling vehicle. So it tells you how they are using it in their supercars, but they're also using it in their relatively low volume production, or relatively high volume production for themselves. It would be classified as low volume for a lot of other companies, but for Lamborghini, it's very much their highest production vehicle, where they're making about 5,000 of these vehicles a year. So this is the fuel cap, and it's being printed on the carbon clip technology. Similar technology, but a very different application, is on Ford's Raptors vehicles, where they've used carbon clip to start making electrical connectors. It's where some of these DLP based technologies can really perform incredibly well in the ability of being able to produce very complex small components for something like an electrical connector. When I say electrical connector, and when you look at it from this image, it looks like a very simple part, but actually within there's lots of very intricate and small components, which additive manufacturing allows us to print incredibly well. Whereas traditionally we'd look at injection molding those sorts of components, due to the complexity and the relatively low numbers of something like a Raptor vehicle, where it becomes worthwhile to use AM for the production. And then also on this slide, we'll also talk about Porsche a little bit, and where they've designed a seat in partnership with Osler around making seat foam lattices. So these are lattice seat foams made out of a TPU material to simulate some of those foams that we would normally use in production. Those foams are obviously, when we're using lattices, it opens us up to the mass customization portal, where we can talk about that in a moment. But at the moment, these are very much a off-the-mill standard component. We are not using anything special here. It's not being optimized to an individual driver. However, that is starting to happen in motorsport, but it's not happening in customer vehicles as of yet. So as I said, that opens us up into mass customization. I expect a lot of the people on the call have probably seen these parts and heard about Mini Yours previously. So Mini Yours was a project run by BMW at the time, where you could customize your own components that were either dealer fit or home fit. So you could have a printed component and you could optimize it and customize it to your own requirements to some extent, and then have it sent to you, and then you could fit it on your vehicle to make it your own. So mass customization has always been is something we've pointed towards with additive manufacturing, and with automotive they seem to work pair hand in hand. However, we're not seeing a huge requirement of the OEMs around mass customization. And if someone was to ask why that is we looked at this as from a JLR point of view, and at the time we just couldn't get the quality we needed out of the components we want to be able to put them on a modern luxury sort of vehicle. However, that obviously fits very well with the Mini options of being able to customize it and having something bespoke to yourself. So there's various different areas where that customization really comes in, or is beneficial or isn't as beneficial, but happily have some conversations at the end around that sort of where we see mass customization going. Prototypes, people often don't like to talk about prototypes because when we're talking about additive manufacturing, people want to see how additive manufacturing can be used in production. Production is often when we speak to either our customers or especially when we're speaking to other people in the AM industry, a lot of the time it's the interest is, oh, when can we start putting these parts in production? When can we start putting these parts in production? And very much when I was doing my PhD, it was we're looking at making these components ready for production. But I think it shouldn't be forgotten about the prototypes. So we can talk about some of the different prototypes. A lot of the prototypes will start from very first. We want something in our hands. Ourselves at JLR and a lot of the other automotive OEMs still use a lot of clay modeling. So we will have a component or a whole vehicle, and we will use a 40% model initially and then put clay on and trying to get it to look right. And then we'll even manufacture full-size vehicles and with clay to get those right. So once we've done that, we can then scan them, and then you may choose to go and print those sorts of technologies. We have at JLR, we have 6 different technologies. So we have polyjet, as some of the conversations earlier were covering a lot of these processes, so I won't go into them with any depth, but we have polyjet technologies, we have stereolithography, we have fused deposition modeling, we have the carbon clip process, we also have MJF and then laser sintering as well. So MJF is technology from multi-jet fusion from HP. But we see with our stereolithography and our polyjet machines, they're very much in high demand from our prototype, from our design teams for their functional bucks. So bucks are what we describe as something that it may go from a very first model that we want to have a look at, get in your hands, how does it feel, how does it look, all the way through to something that can kind of be pushed along. We might push it so it's outside, so we can view what the vehicle looks like in the outside, because obviously the light changes and that therefore changes how we perceive vehicles. So I would say on something like your lithography or your polyjet machines, like 95% of those, the parts we manufacture in-house are for those buck sorts of models. And then when we're talking about functional prototypes, I would say the majority of the components we print at JLR are for functional prototypes. We do print some production parts, and we can talk about that, but the vast majority are functional prototypes. However, what we expect our functional prototypes to do is act like a normal vehicle. We may make, for instance, you can see this camouflage vehicle is currently sitting in a MVH cell. So we'll be doing noise, vibration and harshness testing in there. But we may make 200, 250 vehicles of that vehicle. And that would be for all sorts of testing, be from hot weather, cold weather, VMAX, so as fast as the vehicle can go, all the way through to, okay, how easy is it to drive along and use the infotainment system? So these parts are expected to handle and act as a full vehicle, and quite often we are manufacturing more of these parts than you will on some low volume production vehicles or low volume production applications. We'll also use them for novel and unusual testing. So on the bottom right is when we were developing the new Defender vehicle, we were finding that dogs were jumping in and out because our vehicles are generically quite tall. When dogs were jumping in and out of the car, they were scraping the paintwork. And so rather than having, and we did get some dogs in to do that testing, but also we simulated some of those dog paws and scanned a dog paw, and also used our materials department to try and match the hardness of their claws as accurately as possible. And then we essentially created a robot dog paw that would then scratch that paint over and over again, which then helped us develop a solution So when people's dogs were jumping in and out of their car, it didn't scrape it as much. I know some people, I'm sure, probably just use a bit of carpet or a rug there, but equally we can look at some materials for a little bit more of a unique solution for that sort of problem. Other applications of polymer AM in the automotive space, and I think this is one where we're really seeing that demand, and we expect this really to be a growth area. I know the Nissan example, where actually there is a metal example, and we've tried to stick to polymer examples here, but it's one worth talking about. So quite often we will, as a business, someone like JLR, we will be expected to be able to service and maintain our vehicles well after they've left production. So for instance, the part on the right hand side, they are seat squabs, as we call them, which are levers that are on the vehicle. They fit cars that were produced from 97 to 2003, I believe. So they are a part that you need to be able to adjust the seat correctly. That they were initially a injection molded part. However, the injection molded part manufacturer who originally made these levers went bust, and therefore that tool no longer exists. We only, as JLR, need about 50 to 100 of those a year. So what we've done is we've actually optimized the geometry on the back end, and there's a reason why we're seeing the front side rather than the back side. So we've optimized the geometry on the back end and made it stronger than the original injection molded part was, as well as then post-process the parts, and then they're sold to customers if they require a seat swab when they go into the service dealership. We only make about 50 to 100 of those a year, as I said, but they more than fulfill that obligation as JLR. And these sorts of applications are only growing as we are still looking at and being expected to service vehicles that there aren't a huge amount for, and we can no longer maybe get the material or get the tool to be able to make those parts continuously. And that's exactly what Porsche have been doing as well for a wide range of their vehicles, where if someone says, I need this part for the car, previously they go, sorry, we don't offer this anymore. But now, by using additive manufacturing, either by taking the drawings that previously exist and then turning those into CAD data, or by taking that original part and then scanning it back in to then create something to work off, being able to supply our customers as expected. And then finally, on some of the applications, these aren't all of the applications, don't get me wrong, but I've tried to group some of the major sectors which we work with in JLR and I see as a trend in the automotive industry, is jigs and fixtures. These can go from some very high performance jigs and fixtures where we're talking about ceramic components or stuff like that used for jigs and fixtures, all the way through to quite simplistic benchtop FDM machines being able to provide parts next to the line when required for our engineers or our colleagues as operators on the manufacturing lines. Both examples, there's, as I said, people aren't quite as keen to say exactly what they're doing as much as once were, but I don't know of an automotive OEM not using some sort of additive manufactured jig or fixture somewhere within one of their production sites. There is also the use of, and it's example here with the BMW in the red vehicle, where actually making tools that are customized to our line operators, where that's for instance a thumb. But JLR have also, we've done demonstrations of using a whole glove where we've manufactured a additively manufactured part and able to press something in, because quite often those can be really hard to press in. And okay, if me or you are doing it and we've only got to do it once, it's not too bad, but you get repetitive strain injuries if you have to do that all day, every day, over and over again. So where we can start to actually, rather than printing a tool that's difficult to use, we can design something around our individual operators that makes their life easier as well as safer in the long run. So hopefully that kind of gives us a brief overview of where additive manufacturing currently is being used. And one of the things when I'm initially speaking to Candice and the team were, well, what's limiting us to further adoption? And then we'll go into that a little bit more depth now. So I think one of the things to say is we all do it. We refer and we use an umbrella term of additive manufacturing, but I think what we need to actually consider is it's much more technology dependent than that, and then we'll go into that a little bit more on the right hand side. And all of these topics, they very are much interlinked, but I think one of the good things we're talking about here, and we're sharing the kind of information and that knowledge between the groups, is it all needs to be underpinned by education. And I mean education in additive manufacturing, in design for additive manufacturing, the whole environment. So quickly go through some of these. So is the materials. I believe currently as JLR we have over 250 different polymer materials approved to go on vehicles, and you'll find hundreds of different polymers on each one of our vehicles. So we're seeing a large growth in materials, and we're seeing a large growth in materials in certain technologies, but other technologies, the number of materials that are available to us are limited. And if we take something like a powder bed fusion technology, we're in general going to have less materials available to us than if we're talking about a vat photopolymerization or a fused deposition technology. But those powder bed fusion technologies may offer us a bigger advantage in cost, especially when we start to talk about maybe not even our production in low volume production or high volume prototype. Some of those technologies, for instance, FDM, if you're talking about large components, as we often are in automotive, I know we touched upon large scale later, but if we're talking about just large format FDM machines, they can become very expensive because they're quite slow, and therefore they're not really suitable for our internal production or external production for either prototypes or true high volume production. Cost, we often come back to the cost point. The cost point, at some point, people are going to point to cost. We may be able to have better performance or better surface finish, or we may be more sustainable, so that cost may not be as important as it once was. We're seeing some of those other driving factors, the design and the sustainability, to somewhat overtaking cost in some situations, but it still is a really important factor there. And it's accuracy as well. Accuracy, when we're talking about various different technologies, will have different accuracy amounts, and we will find there's ways of improving that. I think one of the first conversations from Martin this morning was talking about how you can manufacture a part, and then once you've manufactured it, if you measure it and then you put it back into the system, you can achieve a better accuracy. And that is something that automotive companies, ourselves included, are doing more and more. However, it's not always the easiest thing to do, and maybe you need a part so quickly you can't afford to do that. You need it to be accurate first time. Surface finish, I think previously a lot of AM technologies have been written off due to the surface finish not being acceptable. I think that's somewhat unfair. We're seeing improvements in surface finish, be that through the manufacture of the parts as well as the post-production of parts now available to ourselves. But we're also seeing a lot of drive from our design teams and the wider stakeholders across our business and and in the general public wanting to know how things are being manufactured, and having to have this perfect gloss finish isn't quite as important as it may have been 5-10 years ago. Sustainability and circular economy is really incredibly important to ourselves at JLR as well as across the industry now. And we'll go into that topic a little bit more in the next slide. But education, I think by education, I mean ourselves as quite often the experts in the field and in our organizations around how we use additive manufacturing, as well as pushing that sort of knowledge to a baseline knowledge across our organizations, be that from design engineers, quality engineers. So rather than going, oh, I've designed this part, I need it to cost this amount of money, and everything else is kind of done, can I print it? And we kind of go, well, you could print it, but I wish you'd had that conversation with us earlier, because if we'd had that conversation earlier, we may have been able to do something more to make it a more viable option for automotive AM. And we see that more and more. But as people are becoming educated in the field of additive manufacturing, those sorts of conversations are happening early enough that we can start to look at how we can apply AM in our production setting, as well as people quite often in our sector. Automotive is moving very quickly, but a lot of manufacturing technology has just stood still for a very long time, whereas we all know additive manufacturing is moving incredibly quickly and has moved incredibly quickly. And therefore we want it to be able to move, and people go, oh, I looked at it 10 years ago and it didn't work for me. Whereas now we know actually it might be able to satisfy you. And it's that constant education of everyone around how AM is so applicable. I'll touch upon this very quickly, but sustainability is really important to us as JLR. There's some quite ambitious targets within the next few years, as well as having a net zero by 2039. That sounds like a long way away, but that will become very quickly, and that's net zero across our organization. So all the way through from digging up the metal or taking it from the recycle bath all the way through to how our customers use the product right at the end. So there's a large challenge of how we can use more sustainable options across our business, be that our products or the way we manufacture things, in how we can become more and more sustainable. Cost. This is often something that people are really interested in because it's important for us. On the bottom left, there is a diagram showing how an injection molding cost model may look like, where we've got a high cost initially, where we're seeing that being due to the tool that we're using being amalgamated into that cost, and therefore as we produce more and more parts, we see a lower and lower cost per part. Whereas in additive manufacturing, I know it's not necessarily perfectly level, but in the sort of scale of magnitude we're looking at here, it is. And we see where we can see break-even points, and that break-even point is obviously very dependent on what geometry we're using, how we're manufacturing it traditionally, how complex it is, and we see all those benefits. We're starting to see examples where you're looking at in the tens of thousands of that break-even point, and we're starting to get examples where it actually additive manufacturing may always be cheaper than injection molding. If you're using the right sort of material and you've got the right geometry. There's going to be a limited number of geometries like that, but we're seeing that more and more. As well as in the top right, we'll just touch upon, on the image on the left is where we were internally about 5 years ago, where we've seen about a 60% drop off in some of our material costs, in how much, or in some of our overall costs of how much it costs us to manufacture a single component. So that that's across the field. We're seeing that in machine cost. I know the pies still look very similar, but that pie is shrunk significantly to see that difference, as well as we're seeing a real drop in material costs as a lot of the machine OEMs are starting to make their machines open source, and there's more competition and there's more volume is driving that material cost down. I think I'm almost run out of time, so we'll touch upon this, and it's how do I see and how do a lot of other people in the automotive industry see production being achieved. So we'll take, for instance, the Lamborghini example of the fuel cap. So these were being made on carbon machines, and the way they did it and reached their production levels, well, they started to make parts in their R&D facilities where you're making one or two components and you're quite happy, you can test them. It allows the engineers to understand those parts, get them very quickly, but you may not necessarily be able to cope with that higher volume production. And then once you've started to clarify, okay, now I want to start using the production, you may move them to a slightly separate bit of the facility where we can start using more and more parts. And then when we're really quite happy with those, when we go into that full production mode, what Lamborghini and what a lot of other OEMs are looking at doing is then taking that out and then using our traditional tier 1 network or tier 2 network, so where we use different suppliers to supply parts in, using those suppliers to provide the parts in. They're used to working with automotive standards, be that ISO 9001 or the more specific 1649, I believe it is, the ITAF rating, which is what we expect currently all of our automotive tier 1 suppliers to be able to provide parts into, as well as looking at, as we're progressing, more and more additive manufacturing standards, which I'm sure there's lots of people interested in this group at how we control that quality of components going in without having to do 100% inspection or something like that, where aerospace are quite often relying upon to be able to get their parts on their vehicles, whereas it's not very viable for someone like in the automotive sector to be able to do that. So just to leave us on final note, is there's a huge range of applications of polymer AM in the automotive sector. I think there's lots of different areas where we can see improvement, and all of those separate areas, they all lead to more adoption. I'm sure they will. But really, if you ask me what the biggest challenge for someone like me preaching additive manufacturing across our industry as well as our company, is that education in AM and being able to apply that more and more. So thank you very much. I'm not sure if we've got any time for questions, but thank you all and hope you enjoyed it.
Thanks very much, Luke. Yeah, I think we do have time for questions. Before we get into those, can I just clarify from earlier in your talk, does that mean someone at JLR's job one day was playing with dogs and having them jump in and out of cars?
Yes.
Sounds like absolutely the job I need.
So so just down the road from one of our engineering sites is where they train a lot of the guide dogs. So they brought trainee guide dogs in to jump in and out of cars.
And is this a common, so for people who might be considering careers at JLR, is this something we might see more of?
Sadly not, because now they've got a robot to do it for them.
Yeah, I did think you'd probably shot yourself in the foot there by creating a robot
I think so.
to do that job. Amazing. That's almost certainly the best story that I've heard from any industry at talks like this. So I think something that was really interesting to me actually was what you mean when you talk about prototypes, because I think for many of us, and it's great to hear about prototypes, but I think for many of us, when we think of a prototype, we do think about that, just have something to hand around. Yeah. But for you guys, it has to be perfect, right?
Yeah, it's really got to be viable. It's got to be it may not necessarily, we might not be testing that individual component to see how it performs. Sometimes we will. Sometimes we will put a printed component on a vehicle and expect it to perform as the production component. But a lot of the time it's there to allow us to do other critical testing as well. So something like wind tunnel testing or cold weather testing. If you haven't got a vehicle ready by December, you can't go, oh, we'll do it in a couple months time, because there isn't anywhere to do that cold weather testing in a couple months time. So it becomes really, really important.
Yeah. And do you find, because I think obviously as an academic, education is a really key thing that I'm excited by. Do you find that people are coming in kind of knowing about these techniques, or do you think that's still a massive problem we need to address?
I think when we talk to our grads or our undergrads or our placement students or our apprentices, I think there's a much wider knowledge of AM and what AM could do and what it has been doing. I think, as I kind of alluded to, with some of the engineers who've been around for a little bit longer, is there's quite often the point of view, I looked at that 10 years ago and it wasn't right, or people will say I looked at it 5 years ago, it turns out it was 10 years ago, and they were looking at an SLA component that they dropped on the floor and broke. So it's that ongoing, especially as the sector moves so quickly, it's difficult enough for someone like myself to try and keep up with how the industry's moving. For people who aren't living and breathing it every day, it's even more difficult. But I think in general, I would say yes, engineers now coming into the business have a much better understanding than they did 5-10 years ago.
And do you think, I'm going to keep asking questions. Obviously, if anyone has questions, pop your hands up or text in a chat. Do you think people coming in are taking advantage of those technologies in terms of design capability? Do you think we're there yet with that, or is it basically doing the same old stuff?
I think that's probably the biggest factor, is people aren't thinking about design for AM necessarily right at the beginning of their process, and that's really to achieve the biggest benefit. It's thinking about it right at the beginning. There are examples of, yes, we can change parts afterwards, but when you've started to commit to this is kind of what a part might look like, it's sometimes too late.
Okay, so the message there would be, come
think about it really early. Yeah, exactly. Yeah. And that's a difficult thing to do, of course it is, but and we're talking mainly about polymer AM here, but that's the same with metal AM as well, and metal AM probably even more so.
Yeah, super interesting. I'm just checking the chat, maybe that everyone's used their good questions already today. We've got a comment from Elizabeth saying it was really interesting. It was nice to see some larger component applications. Not surprised there, and agrees with the limitations you highlighted. So Martin, who spoke this morning, says weirdly he's seen the opposite recently, sometimes with students using PLA and cheaper materials or processes and getting a poor opinion. Yeah,
I think that's a good point, Martin. I think it's one of the things we try to do is dispel some of those myths, where people are, there's a vast difference between some of those hobbyist level machines that students may have got to play with at one time or another, because people are reluctant to often hand over the keys for hundreds of thousands or £1 million worth of machinery to students. But it's quite often, yes, this is what you've done, but if you did it this way, look how much nicer it is.
Well, and funnily enough, we had the opposite. I've lost track of opposites now, but we had the opposite many years ago when one of our PhD students showed I think it was off our MakerBot system, showed a part to our head of faculty at the time, who was really amazed and went, oh, I didn't realize these processes were such good quality now. That was really interesting, because we obviously would naturally see the defects and the stair stepping and the surface finish and all of that stuff. But to him, he was like, oh, that's much better than I expected. So there's definitely a perception thing there.
One of the things I do is I carry around not a very good hobbyist level part, around with me in my bag and show it to people, and they're like, oh, that's 3D printing, and then show them something that's been optimized and been built on a slightly different process, and you see a lot more of that. Oh, okay, this is what we can do now. There is a lot of, and I see it as people in this room, his job to kind of dispel some of those myths and really show how we can use AM going forward.
Well, I think that's an excellent point. Oh, sorry, there is a question. Someone said there's a question further up in the chat. Can someone reshare? So I got kicked off for about 60 seconds during your talk. So I think there should be a question from Julan Wu, if someone could repost that question, or if you can see it, Luke.
Thank you, Luke. Really interesting to see the wide applications of polymer AM. What applications would be potential for metal AM in automotive industry could be widely used in the near future? So there's a huge amount of applications, so there's lots of different people using lots of different things. If you're interested in that sort of area, Julian, it's probably worth looking up a vehicle called Zinger. It's spelled CZINGER. So, and I will put that in the chat. So they are Czech/American, and they're using a huge amount of metal AM in their production vehicle. They're talking about a hypercar production level vehicle here, but they're using a lot of metal AM in that. There is also, we're seeing more and more applications, be that in powertrain, so maybe in electric drive unit housing as we go into electric development, as well as in areas such as your chassis and subframes. Next door to us, if I stood in the right location of the car park, I can see their building. Aston Martin have said how they're going to start using metal AM in some of their production vehicles. Initially very low run production vehicles, but we're seeing that across the industry. Lots of very interesting applications there.
Wonderful. We've got a couple of more questions, which I think we've got time for those.
Okay.
So Adelit has said, many thanks for a great talk. Does AM have potential in prototyping and fabrication of solid state batteries for electric vehicles?
I'm by no means an expert in that. There's definitely going to be in the jigs and fixtures of the tooling. When we're talking about some of our solid state and batteries, the sorts of charging rates and dissipation rates we're talking about in those factories means stuff gets really hot. So metal AM and AM in general is going to have quite a big opportunity around heat exchangers and components like that, where we can see really good use of heat exchangers. And jigs and fixtures, it's going to be, that drive will be more and more jigs and fixtures will be built in AM, especially as AM gets larger on large scale applications and stuff like that. So Mark, hopefully that answers your question there. Mark, you mentioned uptaking customization options was hindered by quality expectations. Do you think that's the only reason? It's difficult to know the true answer to that, Mark. I think that's where we got to internally within JLR. But it almost certainly won't be just that solution. But I think quality was, especially when we often think about customization, we're talking about, even for us, it tends to be at our highest value and our highest discerning customers talking about that customization. So that quality becomes more and more important. Sometimes with those sorts of vehicles, quality is more important than cost. So quite often you might point to cost in that sort of area, but quite often quality might even become more important there.
Wonderful. Well, I think we've definitely got a great deal of comments out of you, Luke. You probably need a cup of tea and a sip for a bit.